Good afternoon. I'm a little late. Hi, everybody. I'm just going to set up my. I was going to say I was going to set up my office, but no, that would be wrong. I'm just setting up my screen. You know, some of these terms will probably like linger through the time beyond pandemic. I'll be in a classroom and I'll be like, let me just set up my screen. And everybody's going to laugh at me like, what the hell is he talking about? There's my screen. There's a whiteboard. What was the chat about? Where is our instructor? Hello. Hello, Carla. Okay. My phone rang in the middle of the last class and the board is still dirty. How are you guys doing? Spring break is around the corner. What's the big plan? Anybody driving?
Stay home.
Stay home? That's boring, man. Come on. At least run around the building. Then just stay home. That's it.
I mean, I don't do much anyway, and there's. I don't know if I do. I mean, if I do stuff, it's not probably gonna be going anywhere. I don't drive, and.
Do you like cooking?
Kind of, I guess. I usually don't cook for myself much, though. It's something I do like for special occasions or other people.
Sounds like I don't know. I have a feeling that Dane is a good cook. Maybe I'll knock on his door during the spring break. I'll be like, I'm hungry. Can you give me some good food? Hi, Gauli. Hi, Juliana. Hi, Devon. Hi, Andres. Hi, Isaac. Hi, Adil. Only those who have your cameras on. I'm partial, man. Hi, Julian. How are you guys doing? Any news? Sebastian, Christian, did you find any other relative of mine, Christian? No?
No, sorry, but I was looking.
Keep looking.
Yeah.
Yeah. You might find somebody who looks like me in South America. What's new? Spring break is happening. Then we have the long exam, hour-long exam or hour and 15-minute long exam. Whatever we study until today, since the previous test, that's fair game. So I'm going to clean up the board and get started. Okay, let's get started. So without any further extension of my introduction, which is very long anyway. So we were talking about stereochemistry in my previous class, as you can see in 128A. So let this go. I had to run home. That's why I got a little late. So I didn't want to get a ticket. I didn't want to drive too fast. Can't afford a ticket anymore while our son is in college. Okay, so ambitious plan today, start talking about NMR. Before we do that, just want to remind you guys about some epoxide stuff, epoxide facts, okay? So cyclic ether, that's a cyclic ether, that's the smallest cyclic ether. It's a big deal because it's unstable. That's why it's a big deal. So we are Chem 128B, and today is March 25th. And we are talking about, we'll just start with ethers, then cyclic ethers, and that leads to epoxides. Epoxides. We talked about one synthesis of epoxide. We did discuss the mechanism, so that's a fair deal. I can ask you about that in the exam. And we talked about its synthesis too. So that's one kind of cyclic ether. So this is the cyclic ether. So if we take, for example, sorry, my bad. If we take this particular guy, you should know what it's called. If I say it's butene, that's not good enough. If I say it's 2-butene, even that's not good enough. You have to say cis-2-butene or Z2-butene. Z means same site, Z is same. That's how I remember. And E2-butene is trans. Trans and E, uppercase E, and cis and Z, uppercase Z. Okay, so this is Z2-butene. So if I take this molecule and if I react it with MCPBA in a solvent, I'm going to skip that. We're going to synthesize this molecule attaching the oxygen from the top or oxygen from the bottom. Okay, so you have to think about this molecule like this. Methyl groups are out, hydrogens are in, they're there, we are not showing it, and the epoxide will look like either this or the opposite, okay? The opposite could be drawn as this is the opposite. You could have also drawn the opposite the other way. You could have played a little trick. This is same as methyl in and hydrogen out. Okay, so these two are same. Same thing. The funny thing is the one on the left and one on the right, they're also same. We discussed it in the last class. Watch the video, look at the pictures if you are confused what I'm talking about. Okay, they're the same. They do have chiral centers. These are chiral centers. This is a chiral center and this is a chiral center. And if you figure it out, it'll either it'll either work out as RS or SR. Okay, let's see. How do you do that? That's fair game. I might ask you, because if we're talking about epoxides and if we're talking about what happens from the cis-2-butene and what happens from the trans-2-butene, then you need to know what the preceding knowledge, acquired knowledge looks like, which is 128A materials, okay? So if I say, figure out the configuration, the absolute configuration or the RS geometry of the two centers, you need to figure that out. So that's one group. This is one group, okay? So that's the smallest group. That's the large, that's one group. This is another group. So that's one. I'm going to color code it. That's one. This is sort of another one. And this is sort of another one. Okay. So which one is the extra? I mean, I always do, I don't do 1, 2, 3, 4. I know that none of you took 128A from me. So you're probably not familiar with that. So we usually label the groups, right? 1, 2, 3, 4. 4 being the largest, 1 being the smallest. The way I like to do, it reminds me of ordering food in the drive-through. I do extra small. There is no extra small French fries. That's the kids' meal. That's extra small. And then I go large, medium, and small. Okay, the other three groups. So the green, the red, and the purple. Okay, one is large, one is medium, and one is small. Let's do a quick review. And you figure it out later on. That's large. This is medium. and this is small. Why? You have already learned it. If you want to relearn it from me, set up an office hours. I'm more than happy to discuss it. Large, medium, small. Large, medium, small. So it's clockwise. Therefore, this stereochemistry is R. I can guarantee you, I don't have to work it out. Because this is meso, you can tell that the other stereo center should be which one, R or S. I am giving you an information that it's meso. If this is meso, if the relationship between this guy and its mirror image is meso, if you know that it's meso because they're the same compounds, what should be the stereochemistry of this center? Should it be R or S if the other side is R? Who remembers? You don't have to work it out like the way I worked it out, large, medium, small, or 4, 3, 2, or 1, 2, 3. I don't know, however you learned it. If one of them is R, the other one has to be something, either the same or opposite, to make it a meso compound. Which one? What did you guys learn in 128? How much did you retain? You guys are scaring me. I don't know if it is pandemic's fault. It could be partly. My motivation has been low. Should it be R or S? Which one is meso? R, mirror, SS, that's one combination. RS and SR, that's another combination. Let's say there is a molecule with 2 chiral centers. So this is one set of mirror images. This is another set of mirror images. Okay, the left side and the right side are identical, like here. One of these couples, one of these pairs is meso, and the other pair is enantiomer. Which pair is meso and which pair is enantiomer? The top pair RRSS and down pair RSSR. Which one is meso? Which one can be same left and right?
The bottom one.
Carla? Yes, this is meso. And this is enantiomer. Thank you. So if that combination is meso, what should be the absolute geometry of the other center without working it out? Don't work out. You should be able to blindly tell me that that's R or that's S. Carla, do you have any idea? Anybody? Go ahead.
S.
It should be S. Because if it is not RS, it cannot be the same compound. So if this is RS, this has to be SR. And if you flip it, S will become S, the right side, and R will become R, the left side. Okay, let's figure it out. Large, medium, small, extra small is in the back. Anti-clockwise, S is correct. If I'm talking like total French, or if you know French, then if I'm talking total Sanskrit, the mother language of most Indian languages, then you should go back and study. Watch the old videos, read the book, talk to me. I'm very lonely anyway. I'm just kidding. I'm not lonely. I talk to myself, so I keep myself company. So if you're totally clueless and lost, you should probably be very worried. That should ruin the spring break. Hope I'm ruining your spring break. If you're clueless and you're like really looking forward to your spring break, then something is wrong. Then there is something very, very wrong with your reaction and action and reaction. Whenever there is an action, there is a reaction. In chemistry, we say whenever there is a reaction, there is no action because we're stuck in the lab. Okay, jokes apart. You guys, I hope you're following what I'm talking about. If we start with this dude, this guy, which looks like back methyl, front hydrogen, and back hydrogen. MCPBA. What we get? Well, you get this guy and this guy. Okay. Back, front hydrogen, front methyl, back hydrogen. Bad planning. Front hydrogen, back methyl, front methyl, back hydrogen. Okay, let's see. This side, the back side looks like this side, right? So oxygen, methyl out, hydrogen back. So this is S, same as here. You cheat. I mean, there is nothing wrong in this. This is legal cheating. So there is nothing wrong with that. You already worked it out. This is not plagiarism. Somebody was plagiarized caught for plagiarism because he took some portions from his previous write-up. I don't remember the context of this discussion, and it came out. I think somebody submitted a publication, and the publisher said you plagiarized, and he said I copied and pasted from my previous paper. How is that plagiarism? It's my writing, and they were arguing about it for like months. Okay, this is S. You flip the stereochemistry here. Methyl is back and hydrogen is in the front. So it cannot be R. If you are wasting your time figuring out large, medium, small, or 1, 2, 3, 4, you're wasting time. If this is R and you're confident that you didn't screw up, this is S because it's opposite stereochemistry. You swapped it. Once you swap it once, one group of elements or groups, then it's R becomes S and S becomes R. So if this is SS, this guy has to be, do not waste your time. This guy has to be RR. This was a crash course on, advanced crash course on stereochemistry. I'm just trying to wake you guys up. SS and RR, there is no way they can be identical because R stereochemistry cannot become S stereochemistry cannot become R. No matter how much you flip and toss and throw it and pick it up, okay? Their relationship is not meso, they're enantiomers. That's it. I'm done with oxygens and carbons and hydrogens arranged in all kinds of funny ways. Sometimes they're alcohol, sometimes they're not alcohol, sometimes they're ether. Sometimes they look like birds, sometimes they look like weird birds that became extinct because they started, after they were born, they started flying in circles. They couldn't catch fish, they couldn't find food, they couldn't even talk to other birds. So they became extinct, not instinct. Okay. I'm going to take a picture. I'll give you guys like a minute to digest what you heard. And then we're going to start talking about NMR. Sometimes we have trouble pronouncing it. I'm not going to mock anyone from the past. Okay, I'm going to sit down and hide from you guys. I might even check my text. You don't know what I'm doing right now. You have no idea. I'm actually doing some meditation with my phone. I'm actually looking for that. Take a look at what you have on the board. I'm just pulling out that presentation for the NMR. Just give me a second. Spring 128D presentations, NMR. I'm going to use the PPT or PDF. I think PPT. PDF, I don't know. Let's start with PPT. Okay. Wait. Let's see. That's the presentation. I'm going to. Okay, so I will go to the PowerPoint presentation by Wade. That's actually a pretty good book. We never used it as a text. Any questions about this chemistry? If you have questions about stereochemistry, set up an office hours with me or bug Mr. Coppage. I will be more than happy to go over it. I love stereochemistry, and it'll be a really good break from my whatever else is going on in life at that time. Something to be proud of at this point in this pandemic. Okay. Shall I erase? Let's start talking about NMR spectroscopy, I guess. I'm excited about NMR. Okay. Last chance to ask me questions. I'm going to minimize this screen so that I can see your pictures. Okay. Hope everyone is still doing okay. So I'm going to erase. That pretty much ends. We can discuss epoxides opening with like acid catalyzed things and static hindrance, but I don't think I'm going to do that. Let's close that discussion. So we're going to talk about spectroscopy. We are back to spectroscopy. This is our second phase of spectroscopy discussion. There'll be one last phase, UV visible, but I don't want to talk about it until we get into like conjugated systems with carbonyl compounds at the very end of the semester, which is pretty close actually. By the way, spring break is next week, coming week, so don't show up in your Zoom, because I won't be there unless you guys want to talk to each other. I will give you guys a little, like, sometimes we use the PowerPoint to go over spectroscopy. I just want to talk something about the basic fundamental principles of NMR spectroscopy. This is, by the way, Michael's favorite topic, and I'm not kidding. He knows more about the physical chemistry aspect of it. He's pretty strong in physical chemistry. So Michael, if you find I'm misspeaking or if I'm saying something completely ridiculous or nonsense, you just correct me. Don't just sit there and swallow it. Don't try to be polite. I mean, you don't have anything to be afraid of. You already set for your future path. Okay, so we're going to talk about. I probably made Michael a little uncomfortable. But that was the whole point. So we're going to talk about spectroscopy again. Spectroscopy. And we're going to talk about NMR. Okay. Which electromagnetic radiation does NMR exploit to function properly? Who remembers? Infrared, UV visible, X-ray, gamma rays, microwave, or radio wave? Which one? Which one? Who remembers from the past? Not from the far past, but this is from this life. Your kindergarten years in 128B. Who remembers which electromagnetic radiation is used in NMR? Same as radar detectors and motion sensors.
Radio waves.
Radio wave. Radio wave. So NMR stands for, what does NMR stand for? No more red, no more something. That actually NM stands for no more.
Nuclear magnetic resonance.
Nuclear magnetic resonance. You sound extremely serious. Nuclear magnetic. Our campus is like a park right now, recreational park. People bring their dogs, their children, they pull out their lawn chairs, they almost barbecue. Nuclear magnetic, there's a gentleman walking his dog. I've seen him before. Nuclear magnetic resonance. Yes. Which medical field technique NMR is almost identical to, as far as the functionality or the principle is concerned? Who knows? I know you know that answer. Most of you know the answer. What is that? Somebody who usually doesn't talk. I want that shy person to speak up today and say that this is the same as NMR is same as this, not someone who I have heard in this course, entire course, somebody who has never spoken. Would you be unshy? Can you unshy yourself and talk? Unmute your soul. Don't keep your soul on mute all the time. Come on, lady or man, boy, girl, dude, dude now. What's the female of dude? I don't know. Where is the shy person? Why isn't the shy person talking? Hello, shy person. Now you're conscious that if I speak, then I will be labeled as the shy person for the rest of my life. He's going to mock me for the rest of my life. I'm not going to mock you, okay? I promise. I will forget about it, this incident, once you speak and I give the answer. What's NMR equivalent to in the medical field? Somebody who hasn't spoken in the recent past. We won't tell anyone you spoke. You want me
It's
to pick
similar. I'm sorry. It's similar to MRI.
MRI, Jaslyn? Thank you for, you're not the shy kid, okay? MRI, yes, that's very similar to MRI. Thank you for speaking. What does MRI stand for?
Magnetic resonance imaging.
Magnetic resonance imaging. It's the same concept. How does it work? Michael, you're not allowed to answer. What, so there is, okay, let's look at the three words. Usually, organic chemists, biochemists, biological scientists, biologists, they're called biologists, right? Yeah. Biologists, biochemists, and organic chemists, medicinal chemists, we usually don't deal with the nucleus. We usually deal with the valence shell because that's the happening place, right? Two atoms coming together, hydrogen and hydrogen, or hydrogen and carbon, hydrogen and chlorine, chlorine and sodium, things like that. Different, they interact with each other in different ways. Sometimes they're very friendly, they share. Sometimes they share, they're not the friendliest people. They try to pull the, the joint account electrons more toward themselves because they're more electronegative. Sometimes they snatch when there is the bully, right? Sodium and chlorine, chlorine snatches its electron. Lithium and fluorine, fluorine snatches the electron, makes an ionic bond. So all that happens in the valence shell. We usually don't deal with the nucleus. But so this is something new, right? So one important point from this discussion is nucleus. Something is going on in the nucleus. That's what we need to deal with. That's one important thing. The second important thing is there is something about magnets. And the fourth thing that's important is there is something going on, resonance. It's kind of like molecular resonance, but it's different kind of resonance. Okay, so I'll give you a little preview of how the way an organic chemist like me perceives NMR, and I wish somebody had told me this same way, the way I think this way these days, when I was an undergraduate student. It very honestly, when I learned NMR, when I was an undergraduate, I didn't remember anything from that learning. I don't know what the teacher was talking about. Maybe I was distracted, or maybe the instruction was done my way. I'm very picky. So when I decide not to learn, I'm like one of those stubborn dogs. I will just not learn. So it's not something to be proud about, but then that's one of my character traits. It's not something good. You should not adopt it. Don't learn from your instructor, not everything. Should only pick up the good things. Okay, so there is a nucleus and something is going on in the nucleus. So let's look at the nucleus. Let's look at the Let's look at the smallest nucleus. Who's got the smallest nucleus with the least amount of stuff in there? What's that? Which
Hydrogen.
element's nucleus is the smallest nucleus?
Hydrogen.
Hydrogen, right? So this is hydrogen. Hydrogen should be written in blue color because I don't know why. I always write hydrogen with blue. That's hydrogen element, right? And hydrogen element has a proton in the nucleus, and it has one shell and it has one electron. Okay, that's the electron and that's the proton. So when you look at the proton, just the proton, okay, there is this proton and this is it, and we call it, what do we call it when we have, when the hydrogen has lost an electron, and this is all that the hydrogen is looking like, nothing but the proton, we call it a proton. Right? So similarly, when we are referring to just the nucleus, we refer to not as hydrogen nucleus because that's mouthful of words. You know, when you are using that word quite often, quite frequently, we can't use that big word. It's the same deal why pK has emerged. We don't talk about Ka because the acid dissociation constant is probably like 2.3 times 10 to the power 10 power minus 7. You can't always say that, yeah, because you know acetic acid's acid dissociation constant is 6.95. I don't know. I'm just coming up with some random number, some like fake number. 6.952 multiplied by 10 power minus 6. Okay, it's much better to say the minus log of that value, which is pKa, and we say the pKa of acetic acid is 4.74. pKa of hydriodic acid HI is minus 10. pKa of HF is 3.2, something like that. Correct me if I'm wrong. pKa of water is 15.5 or 15.7, depends on which book you look at. So the same reason we call this guy the nucleus. This is just the nucleus. And we lovingly call it a proton for this particular guy when there is only one proton there, right? For hydrogen, we call it a proton. So oftentimes we will call it proton NMR. We say proton NMR because in this particular case, we are focusing exclusively on looking at different types of hydrogen nuclei. One nucleus, it's not an English course, and I'm not an English specialist. I'm not great in English, but there are a few things that annoy me. One thing that annoys me in the hallway when I see a student with 2 gloves and touching a door handle, it really gives me blood pressure, hypertension. Another thing that I don't like to hear or I don't like to read is one nucleus. Okay, that's nucleus. Multiple, when it's greater than 1, it's nuclei. Okay, nuclei. So little English interjection, but try to remember that. Okay, this is a side discussion. Okay, so we're talking about proton nucleus, and why are we talking about nucleus, and what does it have to do with this technique, and why has it become such a big deal since the middle of the 1900th century, the 20th century? Okay, before 1950s, NMR did not exist, and after NMR has been, I wouldn't say invented, it's kind of right, but then after this technology has been developed and has been commercialized, and we have been using NMR instruments, it has become like the screwdriver of a handyman or the saw of a carpenter or like a wrench of a mechanic. I mean, without NMR, I feel crippled. When I took up this job like 12 years ago in 2008, I interviewed on 22nd of March and I got the offer after some time. I had to fly from India. We were in India at the time. We went back to India, then we came back. It's a long story. So anyway, so I was very nervous, like if I could function here with my research, because we only had an old NMR instrument, which is called 200 megahertz NMR. There is a big magnet, and the magnet was kind of weak in my view. I used to work in a company, and they were like very expensive NMRs. And NMR instruments are some of the most expensive instruments. So usually it depends on the size of the magnet. If the magnet is 100 megahertz, it's about $100,000. If the magnet is 200 megahertz power, that Tesla wise, you know, the unit that you measure is magnetic power. If it is 200 megahertz, 200,000, 500 megahertz, 500,000, 600 megahertz, 600,000, something like that. Okay. We are finally, right now we have a 300 megahertz and a 400 megahertz. Michael knows everything about them, and he has used them to do some really fancy studies, like doing variable temperature NMR and 2D NMR studies. He's really good at it. I'm not just teasing him or mocking him or anything like that. I mean what I'm saying. I don't joke about someone's capabilities. We are finally getting a 600 megahertz. I don't remember how much it costs. The cost may have come down, but they are some of the most expensive instruments you can think about, and you have to like position the magnet. The magnet is like the jet engine of a jet plane, the most refined, the most delicate, and the most robust part of that whole package. Okay, so like the jet engine, some parts have to be made by hand polishing, and you cannot use any robotics. Similarly, the magnet of an NMR instrument you cannot just use all 100% robotics to build it. I think certain parts have to be kind of polished or rubbed, or you generate the magnetic field, and that has to be done by a handful of people in the whole world, and only a few companies make that. So it's becoming almost like an extinct art or methodology. Okay, it's a big deal. So you can tell that how passionate I am about NMR. Okay. So the nucleus. So what about the nucleus? So certain nuclei, certain elements nucleus have they act like a magnet. Okay, I'm going to write it down. Michael, feel free to correct me if I'm saying something wrong. Okay, because I know that a physical chemist or one who is pretty good at physical chemistry or physics, they will never feel comfortable when an organic chemist dumbs things down and talks about some physics phenomenon. Dr. Krishnan probably feels very uncomfortable. He's my collaborator and a good friend, but we collaborate on the project that Michael has been working on. But I'm sure I make him feel very uncomfortable sometimes the way I describe certain event or phenomenon. Okay, so I'm going to speak like an organic chemist. I can't hide it. I can't wear a wolf's clothes and look like a wolf. I'll still be barking or meowing. Okay, number one, bullet point. Certain nuclei have magnetic property. Okay, if they have odd number of proton and or neutron. Okay, if they have odd number of proton and or neutron, they have, this is all physics. Do not ask me questions about that, because either I'll have to lie and basically fake my answer, or I'll have to like surrender and say, I don't know, I'm sorry. Okay, I'll probably take the second route. You can ask Michael, he probably knows. Okay, when they have odd number of protons and or neutrons, they develop a magnetic property. So what do they look like? Like imagine like a bunch of insects. There are a whole bunch of hydrogens. Let's say you have a balloon filled with methane gas. Okay, there is a balloon, okay, tied with a string, and it's filled with methane gas. And each black dot is CH4. Okay, so there are a whole bunch of hydrogens in that system, right? There's a methane molecule here, everywhere in three-dimensional disposition. This room is, let's say, this is the balloon, a cross section of the balloon, and it's filled with methane gas. So methane gas has these hydrogens, and each hydrogen has a nucleus, right? So each hydrogen has a nucleus. So when you have a whole bunch of hydrogen nuclei in the vicinity, in a sample, in the NMR, you have to put the NMR. This is what they look like. There was one outside. The NMR tube looks like this. By the way, Michael, if you need more NMR tubes, I have it here. I don't know where they came from. So this is how the NMR tube looks like. Okay, you make a I'm going to drop it. I'm not getting a good grip. So this is how the NMR tube looks like. Okay, I'm trying to look at my own screen. This is how the NMR tube looks like. A little more than 6 inches. How long is this? Maybe 7 or 8 inches long. And then there is a cap that goes on top of it. This is like a little plastic cap. Okay, it looks like that, like a little plastic cap that fits on the top. You take your compound, whatever compound. Methane is going to be hard to do because methane is a gas. Let's say you have hexane or octane or some compound, benzene. You take like very little amount, like a few milligrams, put it in here, and then dissolve it in a solvent. We will discuss the solvent of NMR later on, because the solvent cannot be just any solvent. You cannot just dump it in methylene chloride or ether or hexane. The solvent has to be opaque to the NMRI, because otherwise there will be too much solvent, and all you will see is the solvent. You will see the weeds, and you won't see your plants, your cacti and your succulents, because the grass is so big. So we have to do some little trick to the solvent so that the NMR doesn't see the solvent. Okay, so you have the solvent about approximately, what's the distance? Little more than an inch, maybe 1.1, 1.2 inch tall. You put the solvent solution in there, which has dissolved a little bit of your compound. How much? It could be 0.5 milligram. It could be less than that. It depends on the NMR. Stronger the magnet, more expensive it is, and higher is the resolution or signal to noise ratio. Okay, so you can get away using very little solvent, like 0.5 milligram instead of 10 milligrams, if you have an expensive NMR. It's as simple as that. More expensive, better is the NMR instrument, most likely. I mean, there could be some exceptions, but generally that's a rule of thumb. Okay, so this is how the NMR sampling tube looks like. The diameter of the tube is probably, how much is it? Maybe 4 or 5 millimeters, something like that, maybe less than that. Michael can correct me if I'm wrong. Some NMR tubes can be very expensive. They're made out of quartz, and the glass has no fault. Like it's perfectly homogeneous, or there could be other properties like how visible it is, or it doesn't have any metals that can cause some aberrations or some problems to the NMR signal. Okay, it's not going to produce any additional signal. So let's say you have an NMR tube. Okay, you have an NMR tube and you have your compound. Okay, you have a solvent, and in the solvent you have the compound dissolved. And I'm not going to use the methane molecule. Let's say you have a compound. Let's use something simple, something that's liquid but has only one kind of hydrogen. How about benzene? Well, benzene, you haven't been exposed to benzene. Any other compound that comes to your mind? Let's draw a compound. We're going to talk about symmetry of molecules and shape of molecules and equivalence of hydrogens in a short period of time. Very soon, it's 4:15 right now. Maybe today, maybe not today. Let's draw a molecule. How about cyclohexane? Cyclohexane is a liquid. Let's draw cyclohexane. Let's say this compound is cyclohexane. Okay. All right. It's cyclohexane. I won't discuss how many types of hydrogens are present in cyclohexane. We will discuss that later, not today. Let's say, for the sake of argument, there is only one kind of hydrogen. CH2, 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 CH2. Let's say there is one kind. You know that's not entirely correct. Let's say there is one kind of hydrogen. So in the sample, you have whole bunch of nuclei. Okay, and remember that the nuclei, depending upon the number of protons and odd number of protons and or neutrons, it develops like a magnetic property. It starts to act like a magnet with a north pole and south pole. So imagine it's not perfectly round. It's got an electrical field, and it's spinning. The nucleus is spinning, and it develops some magnetic momentum. So if you're generating an electric field and magnetic field, they go hand in hand. Remember that cobbler's tool, the three finger directions. You may have learned it in physics. Okay, so imagine cyclohexane is in your NMR tube, and Michael has just put that NMR tube inside the NMR instrument, which we will discuss later on. Okay, and imagine that there are a whole bunch of nuclei. The nucleus of each hydrogen, they're all here, right? So I'm just going to draw like a cross section of that in 2D. Let's say this is one nucleus. Okay, this is another nucleus. This is another nucleus. And because they have developed a magnetic field, they have a direction, north and south pole, right? Like if you have a bar magnet, and if Earth's magnetic field is missing, if you could turn off the Earth's magnetic field, and if you hang those bar magnets using a string from the middle, one will point at you, one will point to your right, one might point up to the right, maybe north east corner, somebody might be pointing down, somebody might be pointing at me. So they will be random if there is no major magnetic field around it. So they're going to be all random. And it's not necessarily 2D, it's going to be in multiple directions. I'm going to just draw 5 of them. Let's say there is one here. There is one here. 1, 2, 3, 4, 5. Okay, 5 is good enough. So they're random. Now, so this is all happening inside the NMR tube. Okay, and each nucleus, if you're shadowing a physician, or if you're shadowing something in the medical field, it'll probably make more sense when you actually look at an MRI. It'll make much more sense because you will be able to understand what is going on. How an MRI sees something is wrong in my brain or in my knee or in my stomach or somewhere else. Okay, what's a right pattern of the MRI image and what's a wrong pattern in the MRI image? Because if it is supposed to be having blue here and yellow here and red here, and mine happens to have the blue patch is much smaller and the red patch is more, what does it mean? Why is that? Well, you have a control, which is a healthy person. You're always comparing a patient's MRI with a healthy person's MRI, and you have an idea, like it's already been calibrated, so something stands out because the color patches are not looking like the control or the healthy MRI pattern. Okay, something like that. So this is all happening here in the NMR tube, and this is NMR, not MRI. MRI is not done that way. And imagine there is nothing else going on. Now, there is no major magnetic field in the vicinity. Okay, this is this. So now what you do is you put this NMR tube in your expensive NMR instrument and the NMR magnet. Okay, this is the NMR magnet. As I said, this is the jet engine of the jet. Okay, Boeing 787, the Dreamliner, has two engines, and imagine this is one of them. This is the heart of the machine. And Michael puts this NMR tube with a little cap on top of it. Okay, he inserts it from wherever he inserts. There's a probe inside. It's called a probe, PROBE, and its NMR tube first gets suspended with compressed air. The air is flowing from down to up. So as you put your NMR tube with a little round thing called spinner, which holds the NMR tube and prevents it from falling down, well, our students in the past have done all kinds of really good experiments with the NMR tube without the spinner, and the NMR tube has gone inside and broken inside the probe. And that's a pretty bad screw up. And because somebody has to go underneath this whole magnet and pull out the probe by turning off a lot of things and from the bottom, and basically clean up the probe with the broken glasses and stuff like that. We have had a student, Michael, you will get a chuckle out of it. Somebody inserted the whole thing upside down. The spinner has a top and the bottom surface. Okay, it's a little bit fatter on the top and a little bit narrower at the bottom. Okay, somebody put the whole NMR tube in the wrong direction and it fell inside because the compressed air could not keep it suspended. And that was another bad moment. We call our technician the sorcerer, because he is really what do you call, an instrument whisperer. He can keep them alive with his magic touch. I don't really know if he has magic wands and mantras and he knows any magic like those movies, but he can keep a dying instrument alive for n number of years. He's a magician, but he's a human. So sometimes when someone does something stupid in the NMR instrument, you can see him so frustrated. But when he's frustrated, he just makes some funny noises. He doesn't use any bad words or he doesn't curse. So it's a bad news for him. So anyway, so the NMR tube goes inside. As the NMR tube goes inside after you insert it, let's say it's sitting inside here, okay, with your sample down here, okay. Now what's going on is this is a magnet. So imagine there is a magnet surrounding it, okay. This is a huge, powerful magnet. Okay, we're going to call the strength of this magnet. Don't worry about Tesla or megahertz or anything like that. We'll just call it V0. The strength of the magnet, strength of this external magnet, let's say that's uppercase B and O, B0. B0 is the external magnet, okay? So now the sample was out, now the sample is in, okay? This is scenario one, stage one. Where are we with time? 4:24. Can we stop the clocks? Now, scenario two, I'm beginning to shrink the size of the boxes because I can see that I didn't plan it very well. Okay. Scenario two, you have B0. Let's say B0 is acting down to up. The magnetic field of this powerful, fancy, spancy, expensive magnet is that magnetic field is like north-south pole is this way. That's not how it may be in the real case scenario. I do not know exactly how the instrument works out and the exact exploded view or layout of the inside of the magnet? I do not know that. I do not want to know that because I know how to use the NMR. Well, now everybody in my group knows. I have kind of lost my skill. But once B0 is there, it's kind of like turning on the Earth's magnetic field, and you're hanging all these magnets. And if that's north and that's south, all your magnets are going to lining up south, north, facing the south end, facing the North Pole, and all the magnets are going to be lining up, right? They're going to be all lined up along the North Pole and South Pole, along the powerful magnet, external magnet. So now all these little guys line up accordingly with their poles, because each nucleus of hydrogen atom, each hydrogen atom has a hydrogen nucleus, and each atom is acting like a tiny little bar magnet. And once they're lined up with that, once they're thrown in that external field, they all line up along with the B0. Okay, this is stage 2. There are several stages. I hope I can pull it off with the limited space on the board. Stage 3, while your sample is sitting inside the magnet, in real life, it's done slightly differently. I'm going to kind of dumb it down because I don't want to make it too complicated. Sometimes it's not how it's done the way I'm explaining, okay? But just be happy. You know that there is something a little sketchy about what I'm talking about, but this is a good introduction to NMR mechanism. Third stage, B0 is still there. I'm going to just move this molecule to the right, cyclohexane. Okay? And we are assuming that they all produce the same signal. So now we do have B0. B0 hasn't been removed. That's B0. Along with B0, you are applying a radio frequency in the opposite direction. Okay? Listen very carefully. Now you're applying the purple arrow in the opposite direction. If B0 is this way, the radio frequency is the opposite direction. RF stands for radio frequency. Why are we doing that? Well, the radio frequency, we use radio frequency for NMR because that packs the exactly correct amount of energy to mess with the orientation of this nuclei of different atoms. Sometimes little more, sometimes little less, because some intrinsically hydrogen nucleus have certain magnetic strength. Carbon nucleus have a different strength. They're weaker, 1/4 the power of this guy. Phosphorus nucleus, N15 nucleus, not the regular nitrogen, they have different strengths. So, but in general, for all the elements and the nuclei we deal with in chemistry, biochemistry, biology, 429, the things that we deal with, the radio frequency range that we use, it's pretty good, okay? It's good enough, it gives you the right amount of, it packs the right amount of energy, excuse me, to mess with or to deviate the direction of the nuclei that are lined up along with the magnet, okay? Depending upon the strong magnet, you guys are facing the window. Imagine this is a kindergarten class and there are 5 children, including myself, and we are watching a PowerPoint presentation during the Zoom time, okay? So we are with B0. Imagine that that's the right kind of force. The B0 is making me, I'm one of the nucleus, one of the nuclei, I misspoke. I'm facing the window because I'm watching something about, I don't know, environment or I don't know, but electric power or something like that, whatever, or motorcycles. Let's say that. Okay. Let's say we are learning about electric motors and electric vehicles and space science. And then I like two-wheelers, and then somebody just brings, there's a door on the behind us, and that's the radio frequency, that's the dark force, that's the dark side, okay? And I'm distracted. So I see somebody pushing a really cool bicycle, another elder kid, and I'm very distracted and I turn around. Okay, I'm supposed to be facing that way, I turn around. So that's the radio frequency. So once the radio frequency is applied in the opposite direction, all the nuclear magnets are pushed in the wrong direction, or not the wrong direction, in the opposite direction. So now these 5 nuclei are pointing down. The 5 nuclei are pointing down. So this is with radio frequency. This is just B0. This is with radio frequency. That radio frequency is overpowering B0 and forcing the nucleus or nuclei to line up with RF in the opposite direction, opposite to the B0 direction, the main magnet direction. Okay. So if I ask you a question, if you think that B0 is the normal and this is the abnormal, which stage 1, stage 2, and stage 3 between stage 2, stage 3, between stage 2 and stage 3, which one has lower energy and which one has higher energy? What do you guys think? When it's with B0 and when it's against B0, which one has more energy in the nucleus? What do you guys think?
When it's against B0.
Yes. So this is higher. Higher energy, and this is lower energy. Okay, higher energy and lower energy. Then what do we do? Well, then what we do is, this is not how it's done in real life. So I'm actually teaching you something wrong, but let me teach you something wrong, because if you do your PhD or master's or take a course on instrumental analysis, you will learn it the right way. But this is okay to learn it in a slightly wrong way, but it's easier to fathom. Then what we do is, from here, stage 4, we turn off radio frequency. So imagine I'm a kindergarten kid with 4 other kids watching something very educational and motivational, and something that's going to make me a great successful human being in the future. I'm not mocking. Okay, it might sound like I'm mocking, but I'm not mocking anyone. Okay, I'm being sincere. I'm learning something good. Okay, I was not very good student when I was younger. Okay, then I see this little two-wheeler, which is not something that I should be watching when I'm learning in a classroom in a kindergarten. So I turn around, I look at that, and the kid says, my mom is calling, I have to go home, and he disappears. Then I go back, right? So high energy to low energy, okay? So what happens to that extra energy? It's emitted, right? So when it goes back from this to this, this is again stage 4. 4th stage, you turned it off. B0 is still there. Okay, B0 is still there. The external field is still there. And all the magnets, the nuclear magnets, go back to their original orientation, the happy orientation. Well. I was supposed to use the PowerPoint. Too bad. So lower energy, higher energy, and lower energy again. So higher energy is more, red energy is more, green energy is less. So as it's going from stage 3 to stage 4, what happens to that extra energy? What is that extra energy? That extra energy is purple. Extra energy is delta E, which is red energy, high energy, minus low energy. Okay? That energy is emitted, and that's the energy that's measured in an NMR run. Okay? The delta E is measured and it's plotted. That's a very dumbed down version of what exactly is being done here. 436. Okay, we still have time. So that's plotted. Okay, and let's say if this is an NMR spectrum, it's not an NMR graph. Do not ever call it an NMR graph, because that's going to make me very angry. It's an NMR spectrum. And again, a little dose of English, one spectrum and many spectra. I'm very sensitive about it because this is what we do all the time in our field. It's kind of like, and you know, if a doctor finds a new resident cannot pronounce stethoscope, you know, say something funny, then it's going to really arc him, right? So one spectrum, and it's an NMR spectrum. It's not an NMR graph or NMR something funny. You don't say anything funny. You say NMR spectrum, one spectrum and many spectra. Okay, so this is an NMR spectrum, a not graph. It's not a graph, it's an NMR spectrum. So in the NMR spectrum, this delta E, after a lot of manipulation and some modifications and some changes and stuff like that, we can spend like one entire class talking about the x-axis. I need to spend some time on describing you what the x-axis, how the x-axis looks like. You know, it's a ppm. What does ppm mean? Okay, so whatever the x-axis is, there is an axis, and you get a peak. Let's say just one peak. We will discuss in details. Let's say this is an NMR spectrum, and there is a peak. That peak corresponds to that energy somehow. That peak is basically telling you that this particular hydrogen in this particular molecule in cyclohexane, this hydrogen has a nucleus, and the nucleus has certain magnetic strength. And in this particular instrument, 300 megahertz NMR in the third floor, room number whatever in Fresno State University chemistry department, science 1, when it's inserted, when it's, you know, aligned against B0 with the RF, this is the amount of energy that it's packing. And when it's going back to the low energy state, when the RF is getting turned off, again, take it with a pinch of salt, when it's turned off, that's the amount of energy that's being released. Now that energy depends on the nucleus. If it is hydrogen, it's some kind of energy. If it is carbon, it's different kind of energy. It also depends on B0. More money. If you're at a community college, you probably have 100 megahertz NMR. I think that's what they have in Clovis Community College. They have some really cool desktop NMRs. They don't have huge magnets, okay? 100 megahertz. We have 300, 400, and now 600 soon, okay? Berkeley, I believe they have 800. They may have a 1 gigahertz. 1 gigahertz is approximately $1 million, actually more. I think a gigahertz, the last quote I heard, Michael, you may correct me if you know the answer. I heard it's like 1.8 million or something.
I don't know the answer in this case.
Extremely expensive. Okay.
Yeah, I don't know.
Super expensive. So if you have a stronger magnet, the value of delta E will be greater. right? So if this magnet is 100 megahertz, the value of delta E will be less than 200 megahertz. 200 megahertz, the value of the delta E will be double. If you have a 400 megahertz, it will be twice as much. 800 megahertz, it will be twice as much. So for the same cyclohexane CH2, you might start getting your peak at different locations if you don't take care of that business along the x-axis. That's why I will spend enough time after spring break, after Tuesday, to talk about the x-axis, so that the peak for cyclohexane hydrogen always shows up at the same place, so that it doesn't matter what strength magnet we have. Okay, that's why we factored the strength of the magnet in that energy. Okay, so that's what it is. So this is the very simplified explanation of how NMR works. It doesn't have to be a nucleus of a hydrogen. It can be the nucleus of a carbon, the right kind of carbon. Carbon 12 doesn't work because it has even number of proton and neutron, I believe. So it doesn't work. Carbon 13 works. Phosphorus 31 works, something like that. Hydrogen nucleus is good. Deuterium, sometimes even graduate students have an impression that deuterium doesn't work. Deuterium works, but deuterium, which has a neutron, okay, one neutron and one proton, it works. But the way our magnets, our instruments are tuned and formatted, or like kind of like worked out, we don't see the deuterium signal in our hydrogen spectrum. Okay, that's how it works out. We can do this. We can discuss these aspects later on. I don't want to overfeed you with too much information. This is probably already a lot of information. What I expect you to know is that depending upon the right property of the nucleus develops a magnetic property, an electric property, electric field and magnetic property. They start acting like tiny little bar magnets. They're usually randomly oriented in 3D, but once you align them in a large magnetic field, kind of like on our, like holding, like hanging a bar magnet on planet Earth, and then they line up with B0. Then you apply radio frequency. That's where the radio frequency comes from. That's why we need electromagnetic radiation to mess with the orientation of the nucleus. And even though it's the weakest magnetic radiation, electromagnetic radiation, it just packs the correct amount of energy to mess with the orientation of the nuclei. They turn around, it's against B0, that's the high energy state. This is the low energy state. Then eventually you turn off RF. That's not exactly how it's done, but let's say we turn off RF and they go back, they relax. It's called relaxation. So high energy to low energy, whenever I go from high energy to low energy, I'm relaxing, and the extra energy from that energy minus this energy is emitted, and that's what is measured, and that's what is plotted after some manipulation. And that's exactly what the NMR spectrum entails. NMR spectrum is entailing different types of signals coming from different types of protons. Now, I just want to initiate the discussion. There is 1 minute, that why sometimes a molecule may have 5 different types of protons. Should you, if you get just one signal from all the hydrogens, all the hydrogen nuclei, this thing is useless. You must be able to distinguish between different hydrogens. So can we have like a 1 or 2 minute discussion? Like, why do you think different hydrogens, let's say you have a molecule that looks like this, just hang in there for like 1 more minute. You guys are getting 1 week off. It's not like my credit, but I'm going to take some credit. So imagine that you have this molecule, CH3, and then let's say there is a chlorine here, and there is a hydrogen here, and then there is a, I don't know, a carbonyl. There is a carbonyl, and then there is a carbon, and then there is a hydrogen here. Okay, so there are 3 kinds of hydrogens. That's one kind of hydrogen. This is another kind of hydrogen, and these 3 guys are another kind of hydrogen. Okay, so this molecule has 3 types of hydrogens: one aldehyde, one next to the chlorine, and one on the methyl group, right? So one has 1 aldehyde proton hydrogen, 1 CH methine hydrogen, and 3 methyl hydrogen. If all of these 3 types of hydrogens produce one signal, if you end up getting in the NMR spectrum of this compound, if you get just one signal, it defeats the purpose. We are developing this expensive instrument to do this expensive study. Of course, you guys understand, even though I haven't told you, so that we can distinguish the aldehyde from this guy from those guys. Okay, so that's the whole point. And the secret is it does. Does anybody have any idea how different nuclei exhibit different magnetic strength? What makes the different nuclei of different protons, like the blue proton, the red proton, and the black protons? How are those magnets have different strength so that one guy shows up here, one guy shows up here, and one guy shows up here? What makes those, the strengths of the different nuclei magnetic property different? What makes the magnetic property different? Anybody? Any random idea? I've
The
never.
electronegativity of the atom that's attached to the, like, that group.
Varun, you mind turning on your camera when you're answering?
Oh, yeah. It's
Yeah.
just like the electronegativity of, like, that, of
I
the
want
atom
you,
that's
I
like
want you
attached to
to,
the.
I want you to explain to your neighbor who has only gone through like kindergarten. How would you explain it to him? Electronegativity, I don't understand electronegativity. Dumb it down. Can you dumb it down for me?
Try.
So you have the nucleus, and the nucleus is a little magnet, and it's feeling the strength of the big magnet. It's kind of like we are standing on the surface of Earth and we are feeling the heat from the sun. And then there is something in the middle, which can be thicker or thinner or intermediate thickness. What are we talking about? There is a shield in between us humans. We are the little magnets and the big magnet up there, which is the sun. There is something in between which can be thick or thin. What am I talking about? What am I hinting at? Anybody? What's that?
The electron in its orbital.
Electron is spinning around, right? The probability of finding the electron could be anywhere along that spherical surface. So that's the shield. You have the magnet, you have the shield, and you have the main sun here, which is trying to shine it with its magnetic field. That's B0. That's the sun. Imagine you are like a little, we are the little humans on the surface of Earth, and that's the electronic cloud. When the clouds are thick, do you feel the sun as much as you feel it when there is no cloud or less cloud? Does it make sense? Can we use our clouds in the sky as the electronic cover, the single electron that's spinning around? So I will tell you why it could be thick, why it could be thin. So that's in between. That's preventing me or you, who is the magnet, from feeling B0. Okay, that's the only shield we have. Now the shield can be thick or the shield can be thin, depending upon what Varun just said. If your electronic environment has extremely electron withdrawing groups, okay, which is felt by this guy, okay, that red hydrogen, do you think the red hydrogen's electronic shield will be thinner or thicker than these guys?
Thinner.
Thinner. So this guy will have thin cloud, and these guys will have thick clouds. So which magnet will act stronger, the black hydrogens or the red hydrogen? Which one will feel the heat more from the external magnet? The red or the black? Which one will be acting like a stronger magnet because it has thick shield or thin shield?
Thin one, probably.
Thin one, exactly. So this guy will be stronger magnet. So the delta E value will be greater when your cloud is thinner, like the sunny days. When it's a cloudy day, you don't feel that much energy. You feel depressed. Some people in Oregon and Washington, in London, when it's always overcast, they're like, I don't know, I don't feel like doing anything. When it's sunny, you feel like going out and dancing around and hiking and whatnot, right? So thin shield is caused by exactly what Varun said. When you have electronegative environment, when you have electron donating groups in the neighborhood, you have a thick shield and you're like a little, magnet that's not really active, okay, a weaker magnet. So that makes different hydrogens develop different magnetic field for their nucleus. I think I'm going to stop right there. I have already gone past the allotted time, so thank you for your patience. I really appreciate it. No classes next week. We will meet on Tuesday, 1 week after the spring break, and we'll have the exam. I do not know if it's going to be free response or multiple choice on Canvas. I have not decided that. And so if you have any questions or whatever, we can email me and I'll answer. I may be out toward the end of the spring break, but I'll be around at least until Thursday. Okay. So have a good weekend. Have a good spring break. I'll make everything available. Before I forget, let me take a snapshot of the board. And we're going to continue with our discussion on NMR for probably more beyond the first week after spring break. Okay. All right, let me switch back to the front camera and see how you guys are doing. How are you guys doing? Doing okay? All right. So please study. Don't completely have too much fun. Have fun, but don't have too much fun. Then that may not be good. Then I'll feel bad. All right, Amelia, bye, Sean, bye, Yasmin, Gauli, Roxana, Saeed, Julian, Michael, Andreas, and Sebastian. Did I meet someone? Dane. Bye, everyone. Take care, okay? Have a good day. Have a good day. Have a good weekend. Have a
You
good,
too.
Yeah, take care. Bye-bye.
You said the test will be on the Tuesday when we come back, or 1 week from the Tuesday that we come back?
No, Tuesday after we come back. So week from this coming Tuesday. Check the syllabus. It should say.
All right.
All right. Bye, guys. Everyone. Take care.
See you.
Okay. Have a good one. Stay safe. Hey, Michael.
Hey, Dr. Mitra, are you going to have NMR on their test? Should I cover that in like my
Whatever we
review?
have covered today, just some basic stuff. Yeah. Nothing more than this. I'm not going to be expecting them to know more. How are you doing?
Pretty good.
Any more news?
Oh, there was another one. University of Washington said no.
Really?
Yeah,
What's wrong with the University of Washington?
I don't know.
They're missing you, man. They'll be missing you. So right now you're looking like, are Urbana-Champaign or Purdue?
Yeah, I'm gonna over spring break. In addition to manuscript work, I'm gonna be trying to decide which school I want to go to.
Okay. No words from Columbia. You can shoot them an email saying that I already have 2 offers, and I'm leaning toward going to one of them. Don't mention the school.
Yeah,
And I'm eager to know your decision if you could expedite the process. You can, there's nothing wrong. It'll be nice
That's
to
a-
have an offer from Columbia, whether you go
that's a
or
good
not.
idea.
Yeah.
I'll send that out to them and also to what other school? I have my Excel sheet somewhere. There's another 2 schools,
That you
1 or
might,
2 that haven't gone back.
Okay.
Yeah, I'll poke them.
okay, so 2 rejections, Northwestern and Washington.
Yes.
Oh, okay.
And 2 acceptances.
Very good, very good, very good, very good. Do you have any particular person in one of those 2 schools that really stands out for your research?
I've got a list.
Okay. But
It's
not
on my
like,
computer.
not like one person that you're.
No, I'm not banking everything on one professor.
Good idea.
Yeah.
All right, sounds good. Family is good. Did you got the vaccine? Yeah, you got the vaccine.
Yeah, we had some issues with the second shot, but we got it worked out. The Walgreens, something changed in Walgreens corporate where they wouldn't let you do
Wow.
your own scheduling, but we got it worked out. So my parents got their second shot, and my brother and I are hopefully going to be getting ours in the next few days. We're waiting for confirmation from Walgreens.
Okay. Now it's like anybody over 16 can get his shot.
You can, yeah, is eligible.
That's the new rule. Okay, sounds good. And any training going on?
Yes, tomorrow might be busy. Friday is usually Adriana and I go in, but it sounds like Wes is going in there with either John or Ozzy or maybe both. I don't know. So their
Okay.
lab could be a little busy tomorrow.
Don't make anyone sick from, or don't
Yeah.
get sick from anyone. Just be very careful. Be paranoid, Michael. Even if you have been getting the shot, you have gotten the first shot. You never know. And there is still so much unknown. One of our son's friends, a parent, he's a physician. He told his son to not get the vaccine, and my knee-jerk reaction was, "What?" But then apparently his argument is that this, as a younger person, you're probably going to fight it off fine. And then what do we know about the long-term effect of these vaccines anyway, right? And they're mRNA based, right? And that really freaked us out. Like, what if there is really some long-term, like 10-year, 15-year, or 5-year, or even 2-year, like after effect from this side effect from this vaccine? It's an mRNA. It shouldn't be a big deal. mRNA's job is to trigger the gene expression. But what if something goes wrong? Will it wipe out the whole, world population, or will it make everyone impotent? There will be no more children. We're just having some random discussions. I mean, that could be the plot of a movie, right? Like, depending upon the pandemic, like something goes completely wrong after everyone takes the vaccine. So you can't really blame people who I usually like to blame, and I usually like to say that they're crazy, they're just idiots, stopping the herd immunity from happening. But there is some truth to this particular case because it was very rushed. The phase 3 clinical trial didn't really exist. There was no phase 3 clinical trial. So anyway, so I'm not trying to like take your sleep away, but then just make sure that you're not growing a nose from your neck or something. I don't know.
Yeah.
Let's see. Anyway, all right. Thank you.
Thank you. I'm gonna go get my SI started.
Okay. Okay. All right. Take care. Okay. Bye.
So yeah, will you be on campus tomorrow or around or doing stuff tomorrow?
I think so. I have no other place to go.
Cool. We'll all be there. Oh, well, actually, we might just miss Wes because Adriana and I go in at like noon, and I think that's when Wes and Ozzy said they might be finishing up as
Okay.
well.
Okay. That's actually a good idea. Like 2 shifts.
Yeah.
Yeah.
Okay, cool.
Okay. Sounds good. Take care. Okay.
See
Good
ya.
luck with your SI.
Thank you.